Hello and welcome to another episode of Physical Phenomena. As always, I'm your host, Tom Trey. Now today, we're going to talk about a new and interesting topic in astronomy called dark matter. First, we're going to go over what it is, how it got discovered, and how much there is in the universe. So, let's start off with a simple pie graph. You and I make up approximately 5% of the matter in the universe as baryonic matter. So, baryonic matter is protons, neutrons, electrons, etc. Now, 27% of the matter in the universe is something called dark matter. And the rest here, being at 68%, is something called dark energy, little less dark matter. Now, some of you may be saying, hey, wait a minute already. These quantities aren't in the same units. How can you relate something that aren't of compatible units? Well, that's a great question. In astronomy, energy is measured in ergs, and matter is measured in grams. Well, I claim that in physics and astronomy, matter and energy are related by Einstein's famous E equals mc squared equation. So, the speed of light here is c squared, m is the mass, and E is the energy. Energy and mass are the same up to a constant, so for an example like this, it's okay to relate mass and energy. Now, we're looking primarily at this dark matter. What is this stuff? And why does it exist? A lot of research is still going into that right now. I'm going to explain quickly how we discovered it. So, we discovered galaxies and galaxy clusters have something called a rotation curve. Now, a rotation curve is basically a graph of their velocity, v of r, over distance r. Now, from a basic Newtonian mechanics perspective, we can predict what this curve is going to look like. We start with the famous F equals ma equation. You can write it in vector form to be precise, which just means that a quantity has certain components. Things are either vectors or they're scalars. Scalars is just a number that scales things with magnitude. Vectors have magnitude and direction. So, if we take this equation, F equals ma, we know that the Newtonian force of gravity is equal to Newton's gravitational constant G times big M, the mass of a big object, little m, the mass of, in this case, our test object, over a distance r squared is equal to the mass times its centripetal acceleration, because these objects are centripetally accelerating, which is just v squared over r. Now we want to simplify this expression. These r's cancel and these m's cancel. So you get an expression that looks like g times big M over r equals our velocity squared. Now we want to solve for this velocity so we can take the square root of both sides. And then we have that our velocity goes like 1 divided by the square root of r. The 1 divided by the square root of r sort of looks something like this. And that's what we would expect to see with a galaxy rotation curve. Now, the interesting thing is that we don't see that when we look at our observations in our statistical model. What we get is, I'll actually draw in red pen so you can see the difference here. What we get is a curve that looks like this. It comes up and then it branches off, give or take. There are some fluctuations there. But we get something that looks like this, which is vastly different than what we look like this. So we know that we get the mass of these galaxies by their velocity curves. Now, these things have a completely different velocity curve, and it looks much different. So, what astronomers said was, well, hey, this isn't right. There needs to be more mass in these galaxies that we're not seeing. We can only see things that are illuminated or illuminated, for instance, luminous objects like stars, or illuminated objects such as dust, which plays a huge part in astronomy. So we get something that looks like this. So the astronomer said that, well, we need more mass in these galaxies. But so they decided to call that mass earlier dark matter. Now, dark matter is just a fancy way of saying we really don't know what it is. In science, astronomy in particular, when a researcher doesn't know what something is called, they call it dark. For instance, it's dark energy as well. And that's just basically saying we don't know what that is either, but we know that it exists. So this dark matter accounts for approximately 6 times the mass of a galaxy, 6 times as much dark matter as there is baryonic matter in a galaxy